Hello, I'm Mr. Craig, and I wish to work out the examples for single replacement and double replacement reactions. Let's go ahead and get right to it. When we look at single replacement reactions, we have to remember the generic equation that looks something like this, where we have A reacting with BC, so we have something, whether it's a metal or non-metal, all by itself reacting with the compound. And what's happening is that if A is a metal, A is actually going to replace B and kick it out, so that on the other side we'll now have AC plus B. And again, this is if A is a metal, and if, looking at the activity series, if the metal is listed higher than that which it's replacing. So if lithium is the element that's standing by itself and it's trying to replace like sodium and sodium chloride, lithium is right here, sodium is right here, so the thing by itself will kick out that metal. Now what's important to note is that you identify the thing that is by itself as either a metal or a non-metal. So we're not going to have a non-metal kick out a metal and have two non-metals together. These are all ionic reactions. So the table you do not have to memorize, you just have to look at and be able to recognize whether or not, hey, that metal that's all by itself is standing alone, it will therefore kick out the thing within the compound. So let's do a couple examples. So looking at the, going a little too fast here. So if A is now a non-metal, then what will happen, actually let's just do this. If A is a non-metal, If A is a non-metal, here, let me get those arrows out of the way. If A is a non-metal, then what that means is it will kick that out, and so now that we'll have Ba plus C. So that's how the reaction will take place, and again, that will only take place if the non-metal all by itself on the reactant side is listed higher than that which it's trying to replace. And we'll see some examples of that here very shortly. Alright, so those are the two generic equations. So let's take a look at our first example. And again, here's what we want to do. Before we actually write out the products, we want to make sure that that actually will take place. So when we look at it, we have to first of all identify, is this thing all by itself a metal or a non-metal? So again, you need to go to your periodic table and ask yourself, well, is that a metal or a non-metal? So let's get out our periodic table if you don't already have it out. So the periodic table, we have aluminum, which is clearly on the left side of the stair step, which means that it is acting as a metal. Therefore, it will try to kick out the lead, and let's see if it does do that. So we go to our activity series, and we find aluminum, which is right here, and lead, which is down here. So the aluminum, which is listed higher, will kick out the lead. So this reaction will take place. So on this side, we'll have aluminum. And again, our non-metal, we're going to leave it as is, so we'll have a nitrate. Now we're not going to necessarily keep that subscript. Actually, I don't want you to keep that subscript. I want you to write the metal with the non-metal. So write it like that. And then we'll have the thing all by itself like that. Okay. Now, once we form a new compound, realizing that it's an ionic compound, we have to check for charges. So aluminum has a +3 charge. So that means that, okay, so if aluminum has a +3, you have to remember what the charge on the nitrate is. So you've had a couple days to refresh your memory on the polyatomics. So nitrate is a -1 charge, which means that we need 3 of those total. So you need to put parentheses around that. So the formula is balanced. Now that we know that A, the reaction is going to take place, and B, that we have our products here, now we need to balance the equation. If you need to do the inventory, that's fine. Hopefully at this point you're not going to need the inventory, because we know we have a nitrate here and a nitrate here. We have 2 nitrates on this side, we have 3 on this side, which means I need 2 here and 3 there. Okay, so my nitrates are balanced and I didn't have to do an inventory. Now I want to balance out my leads, so I have 3 leads over here. That means I need a 3 there. Here I have 2 aluminum, which means I need a 2 there. And so there's your balanced equation for your single replacement reaction. But again, remember, when you're working these out, identify what that is by itself. Now, I can have these guys switched, so I could have had the lead nitrate over here and the aluminum over here. Just remember that that plus sign just means and. Let's take a look at the next example. Well, looky there. We've got something very special here. So Cl2, again, look at your periodic table. Make sure you identify where the Cl is at. It's over here. It's a non-metal. So when we look at that non-metal, then we have to recognize that we are not looking to replace the copper. We're looking to see if this will replace the iodine. Okay, so we're looking to replace the iodine. So if this does take place, the iodine is going to be kicked out. So let's see, is chlorine listed higher than the iodine? And it is. Chlorine's here, iodine is here. So that means that the chlorine will kick the iodine out. So on the product side, we're going to have Cu and Cl, and then the iodine will be kicked out. Now again, iodine ends with that INE, so that means that it's diatomic. So we'll have a 2 there. Now we do need to find out what the charge on the copper is on this side, because again, we want to make sure that the charges remain the same, knowing that iodine has a -1 charge. Remember, these charges are still intact there. So it has a -1 charge, which means that if I have -1 and we have 2 of those, I have 1 copper atom, so that means it has a +2. Also recognizing that chlorine is also in that same column, it has a -1 charge, therefore we will need 2 chlorines. Looking at, now that we have the formula balanced and we have the correct iodine written out correctly, check to make sure the number of atoms are the same. 2 chlorines, 2 chlorines, 2 iodines, 2 iodines, 1 copper, 1 copper. So that's balanced. So we don't have to put any numbers in front of these, which is nice. All right. Here we have silver, which is obviously a metal, so it's going to try to replace the calcium. And let's see if it will be able to do that. So we check our activity series and we find out, okay, oops, let's get rid of that. So silver is way down here and calcium is way up here. So since silver, the thing that is all by itself, is listed way below the calcium, this reaction will not take place. Now, if you're a good student and you're already anticipating that it would take place, and maybe you went ahead and you said, oh, okay, I see, we're going to have silver and iodate, and then it's going to kick the calcium out, and then you go and say, oh, well, that's a +1 charge there. Silver's +1, iodate's -1, and then you're like, okay, well, before I balance it, or maybe you do balance it, and you say, okay, well, I've got 2 iodates, so that means I have 2 of those and 2 of those, and we're balanced, and then you go check, and you're like, oh, shoot, no reaction. Don't erase it, just simply draw a line through it and write NR. That's if you write this up. If it is a no reaction, and you know it's a no reaction, don't do this. But if you do that, don't erase it, just draw a line through it, strike it out. Okay? So in some of these cases, you will have a no reaction, because again, the silver simply cannot replace the calcium. Even if you say it does here, strike it out and write NR for no reaction. All right, let's look at example number 4, and these are dealing with the double replacement reactions. So with the single replacement reaction, let me zap these guys real quick. Okay. With single replacement reactions, you have, again, that generic equation where you have one thing by itself reacting with a compound. Well, here in double replacement reactions, we have our generic equation that looks something like this, where you have AB reacting with XY. And what's going to happen here? This is our double replacement reaction. The metals are going to switch places. So on the product side, you're going to have A now with Y, and you're going to have X now with B. Okay? So, and if you are upset that I wrote the AY first and XB and you want to flip it, not a problem. Just make sure that you realize these are metals. They must be written first. They're switching partners with the nonmetals. So you have to be aware that you're having, these are all ionic compounds. A metal must be with a non-metal. A metal must be written first. So be sure that you do that. Now, what's also unique about these type of reactions, they will switch. But what we need to do is we need to look at our table for our double replacement reaction and realize this is a totally different type of table than from the single replacement reaction. And the key thing that you want to look at on this table is these two terms here, soluble and not soluble. Soluble means that if I take two liquids and pour them together, they will not react. In other words, it looks like water and it remains like water. Let me do an example here. Alright, so let's take a look at an example. I've got 0.5 molar zinc acetate here, and I also have a 0.1 molar of aluminum sulfate here, and I poured these out. And I have these two liquids that look relatively clear. They look like water. If you look at it in the camera, it looks relatively clear, nothing exciting there. You can see right through there, or at least I can at the camera there. So nothing exciting. When we look at the reaction, and that's the way that all these solutions will start off. They'll look clear. They will look like water. Some of them may have a color, but again, being able to see through it means that it's soluble. Soluble means that when I look at this solution here, and I say to myself, are there any particulates floating around in there? Absolutely not. So that means that everything that I placed in that solution is dissolved, and it's actually surrounded by water, which makes it an aqueous solution. So what we want to do is, we have our two reactants here, our zinc acetate and our aluminum sulfate. We want to do a double replacement reaction, which means that in this case, that these two metals are going to switch places, and we will now form zinc sulfate and aluminum acetate. Now I'm going to speed things up here just to balance out charges. Okay. And what we want to look at, and this is not balanced by any stretch of imagination, but for the sake of the demonstration, and I'll come back and balance this here in a second, we want to look at the table and ask ourselves, and we only are concerned about the products. The reactants are always going to be soluble. So we want to look at the reactants and ask ourselves, do we have a reaction? If you mix two solutions together and it gets cloudy, or you can't see through it anymore, a color changes, heat's given off, an explosion takes place, which we won't do in here, then we have a reaction. But if we mix two solutions together and it gets cloudy, then we have a solution that is considered not soluble. In other words, the particulates in this solution are no longer able to be dissolved in the water, the pure water. So in the first example, I have zinc sulfate. So here's how you use this table. Here are the nonmetals on the left-hand side of the table, and there are more solubility rules than what's listed in this table, but this will be the table that you will use. So your nonmetals are here, and they have their charges, and then here are your metals, and what we want to do is we want to construct our compound, and then once we've constructed that compound, it'll tell us whether or not that solution is soluble, which dissolves in water, or not soluble, which means that it forms clouds. So the first example, what was it? Zinc sulfate. So if we look at zinc sulfate, first thing we want to do is find the sulfate ion, which is right here, and I'm going to blow it up just a little bit. So sulfate is in this row right here. And what we want to do is we want to come across and we want to find anything that is listed here. So we start off with zinc. Is zinc listed as calcium, strontium, barium, radium, silver, lead? No. Is it any other positive ion? Yes. If it's not one of these metals up here, then we say that it's any other positive ion, which means that it is soluble. Soluble means that this zinc sulfate is not forming a precipitate or a not soluble situation. Okay? So the zinc sulfate is doing nothing. It is not forming a precipitate, so we don't have to focus our efforts on that one. Let's look at the aluminum acetate. So when we'll get it down, find your acetate, and it'll take you a little bit of time to get acclimated to this. Acetate is right here. Now it's written like this, CH3COO, but it's still the same thing as this with a -1 charge. This is more the organic way of writing it. This is the way that we write it, which is tomato, tomato. They're the same. Okay? So you find the acetate, you come across is aluminum any positive ion except for silver or mercury. The answer is yes. So in that case, it is soluble, which now means that we have two things that are not forming a precipitate. If both of these products are considered soluble, you have a no reaction. That's one reason why I didn't want to balance it. Now, what does not soluble look like? Well, here's my two solutions. And if I take these two solutions, and I'll kind of get close here and I'll turn these so they're not in the way. If I pour these two solutions together and I don't get a cloudy substance, in other words, as I'm pouring this, nothing's happening. Still looks the same before and after. So in this case here, this scenario is a no reaction. And that's what our reaction tells us. Nothing should happen. Okay? Well, let's look at a second reaction. And again, if it's no reaction, you don't have to worry about balancing it. You don't have to worry about writing the products. But it's probably a good idea to write the products out and to balance the formula. That's what I'm going to check for. And then when there's no reaction, then you don't have to balance the coefficients. Let's look at a second reaction. Here I've got calcium chloride and lead nitrate. So I have calcium chloride, I have a 1 molar calcium chloride, and I have a 0.5 lead nitrate solution here. Okay. And those two solutions look very, very similar to the last two solutions, where they look clear. And there's nothing really exciting going on there. They are both together. Okay. So again, let's write our products. What's going to happen is the lead and the calcium are going to change places. So on the product side, we'll have calcium nitrate. And the reason why there's two is because calcium has a +2 charge, and lead chloride. And again, the reason why there's two chlorines is because lead has a +2. So these both have +2 charges. So let's see here. Let's take a look at our solubility rules. So the first one, is calcium nitrate. So we come over here, we find nitrate. Nitrate's right here. Is calcium any positive ion? Yes, it is. Soluble means nothing is going to happen. Okay. So now let's look at the other scenario. Here we have chlorine, bromine, and iodine. So all three of these apply to this criteria. So it's not like iodide has nothing. All three of these elements, chloride, bromide, iodide, will react in the same way with these. So we come across, we have chloride. Do we have silver? Oh, there's lead, lead +2. Okay. So that means that we're going to go across to this row, and that means that we now have a not soluble. Ooh. Not soluble, this doesn't do anything. Not soluble, you want to circle it and write PPT. Actually, let me do that again. Circle it and write PPT. What that means, we have a reaction. And when we look at the reaction or the things that's being formed, that is what's being formed. So when I take these two solutions, and let me turn it so that little white thing's not in the way. When I take these two solutions, they look very, very clear. Let me get close here. So when I start to pour it, and again, they are clear. I can see right through there. Those are transparent. When I start to pour, if we have a reaction, then we should start to see some clouds forming. And look at that. You can actually see the cloudiness. It's no longer transparent. It's kind of milky white right now. And it's very, very hard to see between that. So in other words, what we have are these fine particulates that are being formed in the solution. And as I add more and more of that, I actually form more of the white stuff that's in there. Now, what is that white stuff that's in there? Lead chloride. Isn't that cool? So in the first scenario, where I took the two together, poured it together, nothing happened. These are the first two. Nothing happens. You don't see any difference in change there. But when I look at the next two and I pour them together and I get that milky white substance forming, I have a reaction. Pretty cool. All right, so that's what our reactions are for our double replacement reactions. Okay. So let's go back to the examples and look at the double replacement. So again, there's our generic equation. All right. So in this case here, we have aluminum bromide reacting with sodium hydroxide, which means that these two metals are going to switch places. So on the product side, we're going to have aluminum with hydroxide, and we'll have sodium with bromine. Again, only bring one thing over. Unless it's a polyatomic, you don't keep the subscripts. Okay, imbalanced charges. It's good habit to get into that. Aluminum has a +3, hydroxide to poly. Trite has a -1, so that means that we need 3 of those. Sodium is a +1 charge. Bromine is a -1 charge. So that one's good to go, as written. Okay, so let's go to our double replacement table. And, whoops, sorry. The first one, aluminum hydroxide. So fine hydroxide. Hydroxide is near the bottom here. Well, let me zap those, sorry. So hydroxide is here. Come across is aluminum and alkali ion. What's an alkali ion? Do you remember what alkali ions are? That's right. Group 1A are the alkali ions. Group 2A are alkali earth. So alkali ions. So is aluminum an alkali ion? It is not. Okay, so whoops. So since aluminum is not an alkali ion, we go to the second row in this same section. Is aluminum any other positive ion? Yes, it is. Which means that we have the formation of a precipitate. So in this case here, this is forming our precipitate. Now, I might be a dirty bird and give you 2 PPTs in the same reaction. So just because the first one makes a PPT, double check and make sure that one does or doesn't. So sodium bromide. So again, we go back to our bromine, which is here. And again, same, all this applies to the same thing. Is sodium silver, lead, mercury, or copper? No. So we go to the second row. Is it any other positive ion? Yeah. Soluble means that it doesn't do anything. So now that we know we have a reaction, okay, we have to balance the number of atoms. So we have the charges balanced. Once we know we have a reaction, we have a precipitate, now we balance the atoms out. So let's do that. Okay, so we have our bromine, our hydroxide, and bromine. So we have 3 hydroxides here. So let's start with that. Put a 3 there. Now it gives me 3 sodium. Put a 3 there. So now I've got 3 sodium, 3 bromine. How many bromine? 3. 1 aluminum. 1. Done. Let's look at the next one. Okay. In our double replacement reaction, these are going to switch places. And we will form barium sulfate. And we will also form, and again, barium is +2, sulfate's -2. Make sure you know those charges. Okay. And the other one is potassium and chlorine. And again, only write one of each unless it's a poly. That's the only time that you ever carry the subscripts over. Potassium has a +1 charge. It's in group 1A. Chlorine's in group 7A. It has a -1 charge. So the charges are balanced. Before we go and balance atoms, let's make sure that we actually have somebody that's forming a precipitate. So, what was the first one? Darn it. Barium sulfate. So find your sulfate and come across. So sulfates here. Is barium listed on this top row? Yes, it is. There's barium. Not soluble. Not soluble means you have a PPT. Okay, so since you have a precipitate, we know we have a reaction, we know we need to balance. But let's double check to make sure the potassium chloride isn't doing anything. Okay, so chlorine. So here we go. Is potassium, silver, lead, mercury, or copper? No. Must be any other positive ion. Soluble. So soluble means it's not doing anything. So we're not going to circle that way. However, we still need to balance the number of atoms. So let's go ahead. I try to start ugly early. Looks like this one's ugly. So we have 2 there. We could start with that one. We have 2 potassiums. Put a 2 there. So now I've got 2 potassiums. Now I have 2 chlorines. I have 2 chlorines, 1 barium, 1 barium, 1 sulfate, 1 sulfate. We're balanced. Pretty easy, right? Again, the hardest part of this whole thing is once you have your products to use this table, and you will be using this table. You have access to this, so don't try to memorize it. We'll save that for AP. But don't try to memorize this, but know how to use it for now. Okay? All right, let's look at the last example. All right, so here again, we have ammonium and lithium. And ammonium is one of our 10 polyatomics, but it does behave as a metal since it has a positive charge. So on the product side, we're going to have ammonium NH4 with the acetate C2H3O2. Both of those do have a +1 and a -1 charge, which is nice. We like that. And then, let's see, lithium is with the sulfide, and sulfur has a -2 charge. Lithium is a +1. That means we need 2 of those. Okay. So before we go and balance the number of atoms out on both sides, let's make sure we have a reaction. So, whoops. So ammonium acetate. So find the acetate, which is right here, is ammonium any positive ion except silver and mercury. Yeah, it's soluble. Now, if we had silver and we had mercury with the acetate, then that means we have a reaction. But again, we're going to say that is soluble, so that means that doesn't do anything. The lithium sulfide, so find the sulfur, which is sulfide right here. And again, we're looking at lithium. Is lithium an alkali ion? In other words, is lithium in group 1A? Bam, there it is. So lithium, whoops, come back. So lithium is in group 1A, so that means that it too is soluble. Which means, since both of these are soluble, what kind of reaction do we have? Correct. You have a no reaction.